So graphically, let's say that I have a put or a call. Let's do a call. And here's the strike. Let's say using the notation of our binomial lattices, I have a US and a DS, and they happen to straddle the payoff function. So I have that the price of the option is the present value of t is, let's say, one step in our binomial lattice, is equal to p star. I'll use the notation from that section, risk neutral probability times c, evaluated at the upstate, plus 1 minus p star times c, evaluated at the downstate. So this is the present value of the expected value of c. In Jensen's inequality, we know that the expected value is somewhere along that line. And what Jensen's inequality says is that price is bigger than or equal to the present value. I'm just sticking a present value into Jensen's inequality. It's a positive number, so that's not a problem. Is bigger than or equal to the call evaluated at the risk-neutral average of stock prices. Which would be, depending on what P is, let's say it's here. So let's say that P is around the half, as it often is, it's around the half, then it's basically saying that the average of D, S, and US is the midpoint. Let's say it's here. Let's say that's the average. And so it's just indicating that the actual price you would pay for the option is greater than what you would pay if you believed that the stock was going to mature at its risk-neutral value. And you recall that the risk-neutral average of stock prices, or you'll see in the earlier chapter, is the forward price. So basically this is saying that the price of an option exceeds the price you would pay if you expected the stock to have its forward value. Another example is arithmetic geometric means. This comes up in various applications, that if you have, say, arithmetic, if you have monthly returns in an investment fund, and you look at the average return, and then you look at the compound return. Well, G is the compound return. It's the return you get from the beginning to the end of the period. A is the average of the end returns. The arithmetic geometric mean inequality says that the geometric mean is never bigger than the arithmetic. And we see this all the time with returns on investment vehicles, that the compound return over the period is always not only less than or equal to, it's usually less than the arithmetic mean strictly. And it's only equal when the returns are equal. And this comes from the convexity of the function minus log x. I won't go through the details, but it's a simple derivation that because minus log x is convex, we can apply that, and we then get this value, assuming a probability of 1 over n for each of the r's. And using the same calculation, a generalized arithmetic and a generalized geometric mean satisfy the same property, and that is where, by generalized, I mean instead of putting the same weight on each return, I can put any set of positive weights that add up to 1, and I'll get the same generalized arithmetic geometric inequality. The final result is one that occurs in the interest rate chapter, chapter 24, whereby we're pricing zero coupon bonds using a result that comes from a Cox-Ingersoll-Ross paper, or it comes from a calculation that was done on a binomial lattice of interest rates, and that is that ultimately a zero coupon bond can be priced by an expected value of zero coupon bond prices. And when we do that expected value, we have to use risk-neutral probabilities. Well, Jensen's inequality, because e to the minus x is convex, Jensen's inequality says this expected value has to be bigger than the exponential evaluated on the expected sum of returns. Well, that means that if I let R0 be the spot rate that gives this price, that the actual spot rate that is provided by our pricing functions in Chapter 24, the emerging spot rates are always going to be less than or equal to the risk-neutral average of the interest rates that are generated by our various procedures.